So hello, I think we can start. My name is Marcel Wild. I'm the lecturer of Group 2. So I planned 3 topics for today. Hopefully we can fit it all in. The first would be trigonometric substitution. That will take the most time, so I take that first. The second would be integration by parts. And the third, partial fractions. Since we missed out on one, I hope one can read it. Since we missed out on one revision lecture, quite a few topics accumulated. So these are not all the most recent topics. Okay, then let's just start with topic 1, trigonometric substitution. We should recall that if you have an integrand with this expression occurring, then you make the inverse substitution x equals a sine theta. If you have something like this, x squared minus a squared, then x equals a sec theta. And if you have a plus under the root, then we make the trig substitution x equals a tan theta. And these crucial formulas, they are in the book on page 526. Now we will start with the following problem, which will also involve quite a few other techniques. So what is the general antiderivative of this function? X times root of 3 plus 2x minus x squared. That, well, the term under the root smells like completing the square, so we have to do that, and afterwards we will do the trig substitution. So complete square first. That means I write 3 plus 2x minus x squared as follows. I would like to have the leading coefficient of x squared positive, so I write it like this, x squared minus 2x in brackets. And now here I can read off how I would complete the square here. Well, I can write 3 minus x squared minus 2x plus 1 in brackets, but then, of course, the equality would not be right because the right-hand side is 1 smaller than the left-hand side, right? I'm subtracting this 1 here, so I need to add it here, and now we really have equality. And I take that 1 together with the 3, and then it is 4 minus this term in the brackets, which of course is x minus 1 squared. And now we see that the only sensible substitution is u equals x minus 1. And then well, then we also see what the x is here. And the dx is, of course, here the same as the du. And now we can rewrite the whole expression in terms of u. X is u plus 1. And under the root, I have 4 minus u squared. And the dx is the same as the du. And now this expression, yeah, any questions? Can you speak harder? Zoom, like this. Is it now big enough? Well, okay, now comes the trig substitution. According to the scheme here, it's of the type a squared minus x squared. And so I make the trig substitution. U equals 2 sine theta. Then du d theta is, of course, 2 cos theta, so the du is 2 cos theta d theta. And the whole thing becomes here 2 cos theta plus 1. And under the root I have, well, it's a little bit of a place problem, 4 minus 4 sine squared of theta. And the du is 2 cos, let's write it like this, 2 cos theta d theta, which comes in here. So let's maybe write it like this, that we take the 4 out of the root and it becomes a 2. So the whole thing will be 2 cos theta plus 1. And then here times 2. And here we have the root 1 minus sine squared of theta. And here I have 2 cos theta. Any questions so far? I should have said here that we have to choose the theta in the right interval, which for this trig substitution, when you take the sign, is minus pi over 2 up to pi over 2. Yeah? Oh. Yeah, thank you. So, then this is, generally speaking, the root of cos squared, which, of course, the root of something squared is always the absolute value of that thing. So that is absolute value of cos theta. But because the theta is in this interval here, from minus pi over 2 to pi over 2, the cos is positive in that interval. Therefore, the absolute value of cos is simply cos. Let's write it. Since we are in this interval here, so that looks good. I have a cos here and a cos here. I have a factor 2 here and a factor 2 here. The 2 I take in front. Maybe I start a new page here. That gives me 4. And then I still have here this factor, cos theta plus 1. And I have the cos squared. Right? These two cos squared of theta, d theta. And now what we do next? Well, we just multiply that in and try to integrate it. So this would be 8 cos to the third. So add this and this together with that gives me 8 cos to the third. And then I have here a cos squared, which comes with a factor 4. Oh yeah. Yeah, of course. This is, yeah, of course. Because this is our substitution, the u equals sine theta. So you should have complained before. Here it's always a sine here. Here, u plus 1 is sine plus 1. Fortunately, I took an eraser with me. So it's sine theta, 2 sine theta. The rest should be okay. Let's erase it everywhere. Embarrassing that everything is filmed now, but that's that's life. So it's here 2 sine theta. And here also 2 sine theta. And yeah. So, of course, that changes then. Here we get 8 sine theta. You write the whole stuff here. 8 sine theta cos squared theta. Theta, and then the cos squared comes with the 4. Take the 4 in front. Is everybody agreeing? Well, now we have to integrate that. Remember what the trick is if you have a product of a power of sine and the power of cos, then you look where is the odd power, and you write everything in terms of the other power. So here we simply make the substitution t equals sine theta. Cos. Then dt is minus sine theta d theta. That means I can here write minus 8, and then I have here my cos squared, which is the t squared. And because of the minus 8, I have to write minus sine theta, which is exactly my dt. So, and here, what is the trick if you have a cos squared? It's a double angle formula. So you have here cos squared is a half times 1. And then you have to remember the double angle here, which is 2 theta. And you have to remember whether it's a plus or a minus. What's the easiest way to remember? If it concerns a cos, it gives you a plus. If it was a sinus, it would give you a minus. So it's very easy to remember. So the cos gives you here a plus. So, any questions so far? Sorry, I still... like this. Well, now we can start integrating. Minus 8t to the third over t. And then here, 4 times a half times 1. That is 2, and that will give me 2 theta. And then I have 4 times a half times cos of 2 theta, that is 2 cos 2 theta. I hope that was clear. Then, well, let's go back from the t to the cos. That would be minus 8 cos to the third of theta. Sorry, this is here, what did I write? That should be a 3, of course. Over 3. The theta is cos theta. No. The theta just at the moment stays a theta. And here it's also easy to read off what the antiderivative is. Obviously, it's sinus of 2 theta. If you differentiate, you will get cos of 2 theta times the inner derivative. So it's sinus of 2 theta. And now, of course, we need to go back from theta to x. Remember how it all started out? This was our original problem. We first made the substitution u equals x minus 1. And we wrote it in terms of u. And then only came the trig substitution, which gives us a theta. Then we even had a t, but we got rid of the t in the meanwhile. So we have, with the theta now, we need to come back from theta to u. And the crucial formula is, of course, this one here. U equals 2 sine theta. So the program now is get back from theta to u. And then it will be easy from u to x. I repeat again the formula that we had. U equals 2 sine theta. That means u over 2 is sine theta. And now you can start drawing your usual triangle with some angle theta here. And if the sine of theta is u over 2, then the u should be here and the 2 here. And then by Pythagoras, you read off what this side should be. It must be 4 minus u squared, and then the root. Why is that? Well, if you square this number, you get 4 minus u squared. If you square this number, you have u squared. Add them, you get 4, which indeed is the square of this. Okay, now from this triangle, you can read off everything that you want. First of all, we can read off what is the theta itself. Theta is arcsine of u over 2. And we also need the cos from here. What is cos theta? You read off in the triangle, the cos is this root over 2. And with this information, we can now express this part in terms of u. Let's write it again. Minus 8 cos to the third of theta over 3 plus 2 theta plus. Now here we have a slight problem. Sine 2 theta doesn't work so well because it's everything in terms of theta and not 2 theta. But we had that trick at least once before. You write sine 2 theta as 2 sine theta cos theta. And now you plug in all the things that we found here. So that must be minus 3 cos to the third. Let's put here the minus here to the 3. So we have 8 times this one to the third power. That gives me the root to the third power, and then I divide by 8. So I simply have that root to the third power, which I can write like this. Right? And 2 theta is 2 times that arcsine. Two sine was, of course, u itself. This is our trig substitution we started out with. So that is u times the cos. The cos is here, that root over 2. And now, the last step is to go back from the u to the x. Remember the u is simply x minus 1. So we put in x minus 1 everywhere, but actually we can simplify this in another way. 4 minus u squared is this expression that we got by completing the square. So 4 minus, this is our u. 4 minus u squared is nothing else than our original term under the root. So we might as well take that again. So it is then this original root, 3 plus 2x minus x squared. Maybe we should put that up. Over to the power 3 over 2. Sorry, no. It's not that. Without the root, of course. Like this. Then divided by minus 3. And here, 2 arcsine u, this we need to write as 2 arcsine of x minus 1 over 2. And this is again my 3 plus 2x minus x squared, and then times u, x minus 1 over 2. Let me just check. So that should be plus the x minus 1 over 2, and then times, let's write it like this, 3 plus 2x minus x squared plus c. Hopefully that is all right. Yes. Speak harder. Oh, well, no, the 8. But first of all, I took the minus to the 3. And here I have 8 cos to the third. But when I have cos to the third, I get here 2 to the third, which cancels out the 8. So that should be all right. Now this is quite a complicated exercise with trig substitution, which also involved completing the square, and a few other tricks like this one here, where we had to write it as 2 times sine times cos. Okay, then let's do another one, which would be integration by parts. How would we integrate something like this? A definite integral from 0 to pi over 3 sine x ln of cos x dx. First of all, we should observe that the sign in that interval is, of course, positive. but the cos in that interval starts at 1 and then becomes smaller than 1. So if you have the ln of a number smaller than 1, it's negative. So the whole thing here is negative. The whole integrand is negative, and therefore the value of this definite integral will be negative. And we will now guess how small is this negative number really without any calculator. So how would that work? Integration by parts means that you have to decide which one you integrate first. All right, one gets integrated, the other one differentiated. You should, of course, try to integrate the one factor which is easier, not this one. Here we don't know how the antiderivative of that would be. So therefore we take this as the f prime and this as the g. And now integration by parts says that I first integrate that. So let me first do it without the bounds. It's a little bit more convenient. Sine x ln cos x dx. This one is my f prime, and this one is the g. So that gives me, this one integrated is minus cos x, and this one stays the same, ln cos x. So this is now my f, and this is the g. The correction term says you take what you just got here by integrating, which is the minus cos x, but now you differentiate this one here, which by the chain rule gives me 1 over cos x times the derivative of cos, which is minus sinus x. Any questions so far? Well, these two minuses cancel out. The cos also cancels out. So all I have here is only the sin. Minus sin x dx. This, of course, gives me the cos. So I have here minus cos x ln cos x plus cos x, because the derivative of cos is minus sine. I can write that a little more convenient by taking the cos out, and we might as well go back to this problem where we have the definite integral. So it follows that this definite integral sine x ln cos x dx is any antiderivative of that function, which we found here. I take also the cos out, cos x times 1 minus ln cos x. This is my antiderivative, gets evaluated on pi over 3 and 0. Now, what is that? Well, cos of pi over 3, that is cos of 60 degrees. If you imagine the graph of cos of 60 degrees is, of course, a half. Put in that a half, and here times 1 minus ln of a half. And then you plug in 0 everywhere. Cos of 0 is 1. And here you have 1 minus ln of 1. But ln of 1 is 0. So how does that all pale out? Here we have a half. And we subtract here 1 times 1. Right? A half, here a half minus 1 is minus a half. And then we have this here, which is minus a half ln of a half. Yeah, thanks for complaining. This is one of the few instances when I like that people complain, because they really have a reason. So, I hope everybody agrees this is minus a half minus a half times ln. But ln of a half is minus ln of 2. So this is minus a half, then plus a half times ln of 2. And now maybe somebody can tell me, how large is this number approximately? Without using the calculator. Well, we know ln of 2 is approximately 0.7. That appears quite often. Yes? Huh? Minus 0.15. Yeah, this is exactly correct. This is minus 0.5 plus 0.35. So you get approximately minus 0.15. This is approximately, which we knew all the way. Well, we knew it would be something negative. It turns out it's only slightly negative. So this is that exercise. And well, I think we stop here.